Welcome. This talk is on effective automated content analysis via crowdsourcing. I am Chau-Wai Wong. I'm going to present together with Xinyan Zhao. This is a joint work among BIT, NC State, and the UNC Chapel Hill.
First, let me talk about the background of our study. Coding, or say semantic annotation by crowdsourcing, has been demonstrated to be effective when measuring relatively objective features, like identifying an object or person in a picture or on a web page. However, latent subjective features have been difficult for crowdsourced coding because of two reasons. First, there is a lack of validated tools to measure complex subjective semantic features, such as different kinds of emotions, news frames, or people's moral reasoning. And the second reason is that online workers' response quality tend to worsen as they work longer, as they want to prioritize their earning in each hour. So this brings about a central question for us. How should we balance quality and efficiency in crowdsourced coding and annotation of difficult tasks? To address the challenge, we propose a quality-aware semantic annotation system. This system has two important features. First, the system can be used to identify qualified online workers. Namely, we can use the system to train and select MTech workers who are capable of and motivated to work on complex coding, since coding subjective semantic feature is a non-trivial task. Second, the system can be used to monitor online workers' performance and provide feedback over time so as to ensure the quality of their responses in a longer period. We tested the system through a task of labeling emotions of tweets related to an impactful crisis in the United States, which is the Flint water crisis. So we consider three types of emotions: negative, positive, and neutral, and a total of 11 discrete emotions. So anger, disappointment, sorrow, fear, worry for negative emotions, satisfy, hope, sympathy, grateful for positive emotions, surprise, and sarcasm for neutral emotions. So we aim to have each tweet labeled 5 times for a total of 9,287 tweets, and this resulted in a total of about 42,000 labels. Now let me go over the detail regarding how the system can be used to generate quality responses through a qualifying process and real-time performance monitoring. First, there is a qualification part. A candidate worker has to get the qualification so that he can proceed to work on the formal coding. In the qualification part, a candidate worker has to go through 2 sessions here. First one is a training session where the candidate worker will be introduced to the background of the studies, the instructions, how we define different emotions, the examples for each emotions. They also have to work on 5 training questions to ensure that they have correct understanding of how we define these emotions. And then after they pass the training session, they will go through a test session. In this session, there is a total of 15 tweets. So one is considered qualified if they receive a score that is above a baseline, and then they would be eligible for subsequent coding tasks. Then in the next stage of coding and annotation, the eligible worker would code a total of 20 randomly selected tweets from a pool in a single task. Out of the 20 tweets, 5 have ground truth labels because we have human experts to provide valid and reliable label of the data, so-called ground truth data. And then based on the 5 tweets that have ground truth labels, we compare the coder's responses and the ground truth labels. We generate a quality score that indicates the percentage of correctly answered questions in a single task. So quality score can be used as a noisy measure of coder's performance. And we also calculate accumulated quality score that is a more precise measurement of coders' performance over time by calculating the mean of their quality scores in each task. So coder is expected to maintain cumulative quality score above 60% in order to work on more tasks. Now let's review results that support the effectiveness of the proposed system. First, our results support that quality control is a must for complex coding tasks involving latent semantic features. First, our qualifying process, the system, can be used to identify eligible workers, and our descriptive analysis shows that only a very small fraction of MTurk workers were actually interested in and capable of doing the complex coding task. It's very important to select a pool of committed workers and increase the quality of the collected data. And second, the real-time performance monitoring mechanism is effective in removing weak performance workers. Our analysis showed that about 11% of the total workers were not able to maintain their accumulated quality scores above minimally qualifying score and was subsequently disqualified from the task.
Our second finding is that the majority voting is consistent with experts labeling. Let's focus on the left figure. The horizontal axis is the average number of votes. The vertical axis is the correlation coefficient. The larger, the better. So as we can see from the figure, as we increase the number of votes used for majority voting, the labels given by majority voting is becoming more and more consistent with the labels provided by experts. We can also see the same result on the left figure. Our third finding is that majority voting results are learnable. We characterize the learnability of majority voting results using the generalization capability of a powerful learning system. In this case, we trained a fine-tuned deep neural network. Let's take a look at the experimental results. 3 columns in the table correspond to 3 different subdata sets for the learnability experiments. The first row of equal weight contains the result for the scenario that each MTurk worker contributes equally to the voting result. With the balanced accuracy of 70 to 80%, we can see that the labels annotated by majority voting are learnable by the deep neural networks. The second to the fourth row contain the results for the scenario that we assign higher voting weights to better performing workers. It is evident that such weighted voting scheme can improve the learnability of the data labeled via crowdsourcing. In addition to the major results we obtained, we also have some interesting observations related to the tweet dataset that we use for the crowdsourcing task. We found that it can be difficult for MTurk workers to find all emotions in a tweet. We also found that workers may unintentionally label their own emotions rather than identifying the true emotions contained in a tweet. Not very surprisingly, we noticed that some tweets are more difficult to label than other tweets. We have proposed solutions to these issues for system design of future crowdsourcing tasks. To conclude, we have proposed a crowdsourcing system that can harvest a large number of high-quality labels for complex coding tasks. We have shown that labels aggregated based on majority voting are accurate, consistent, and learnable. We welcome you to visit our poster for detailed discussions. Thank you.